DKW Physics. I'm Mr. McConley, and we've been working on vector problems, vector addition problems, and we've done a few different scenarios. Scenario number one, the vectors met at 90 degrees to each other, so we used our 90-degree triangle rules, and we could solve. Scenario number two, they did not meet at 90 degrees, and we did a sine problem where they met at funny angles. I think it was 120 maybe. But in that case, the two sides that we were looking for were the same length. So we could move things around, we could split it in half, and we could solve. Scenario number three, the hardest scenario, is what we're going to do today. Now we have two things that do not meet at 90 degrees, and they're not the same length. That causes a lot of problems, and we have to do quite a bit of work to get to the answer. So, the scenario is two people pull on a card, or whatever, I don't care what they're pulling on. They use separate ropes. One rope exerts a force of 300 newtons at 35 degrees. That's drawn here. Here would be your 35 degrees. From east. East being to the right. The other exerts a force of 160 newtons at 160 degrees from the east. So again, if that's the east, 160 degrees is this way. And if this is 160 degrees, this leaves us with how much? Okay. So you have 160 newtons pointing that way, and 300 newtons pointing that way. And the problem is, they're not the same length, they don't meet at 90 degrees, so it's kind of a mess and I don't know what to do. All my other techniques aren't really going to work. But the first thing I want you to visualize here is where would the resultant really be? Well, if I move these so they're tip to tail, like if I took the 300 and I moved it over here, I think my resultant would end up being something like that. So in the end, when I get done with the problem, my resultant's going to point something like that. But it's way too early in the game to really have that on the picture because I'm just not ready yet. So here's what you do. You have to look at these two vectors and individually find the x and y components. What I mean is this. If you look at, let's ignore the left-hand side, and let's look at this right here. If I look at this triangle right there, I can make myself a little right triangle, and I can solve for what we call the x and the y components of this right triangle. So let's do so. If we're looking for the y component, we're going to do opposite over hypotenuse as the sine. Sine of theta is opposite over hypotenuse. Sine of 35 degrees is y over 300. So when I use my calculator and I solve it out, what do I get here? I get 172.1 newtons. Okay, so I know this is 172.1 newtons. Similarly, if I want to solve for this x component right here, I'm going to use adjacent over hypotenuse. I'm going to use cosine. So the cosine of theta is the adjacent side over the hypotenuse. Cosine of 35 degrees is the x over 300. So when I solve out for x for the cosine of 35, I end up getting 245.7 newtons. This here is 245.7 newtons. All right, fine. Now, if I do the same process on the other side, taking this right triangle and solving for this x and this y, I can again use sine, which is opposite over hypotenuse. So we have the sine of 20 degrees is y over 160 newtons. That'll tell me that y is actually 54.7 newtons. It's 54.7 newtons. And using cosine to solve for the x right here, cosine of 20 is adjacent over the hypotenuse. So I actually find that the x will turn out to be 150.4 newtons. Well, let me stop right there, just for a second. You know, whenever we do physics, direction matters, and especially with vectors. And if you look at this x, the blue x, and it's pointing that way, and that's a 245, and you look at the green x, and it's pointing that way, and it's 150, they can't both be positives. They're going two different directions. And normally, I like this to be the positive direction, and left to be the negative direction, up to be positive, down to be negative, and I'm going to stick to that plan. So the 150, although it didn't come out that way in your calculator, I'm going to make it a negative. Because that just helps me keep track of my directions. That sound good? Well, the next step is, now you have two different y's and two different x's, and you want to sum them. So what we want to do is we want to say the sum of the y's is equal to, and it's going to be 54.7 plus 172.1, which the sum of the y's will therefore turn out to be 226.8 newtons. Okay? Just go along with me. You don't know why you're doing this right now, but we're summing the x's and the y's. And then we're going to sum the x's. Now be careful. Remember, this is a negative 150.4, and this is a positive, so be clear that you do have to pay attention to your positives and negatives when you're summing them up. And that will give us 95.3. Now what do those two numbers mean? Well, I'll tell you. Those two numbers will actually help you find the resultant. This is telling me if I go 226.8 newtons in the y direction, and then I go 95.3 in the x direction, that is where my resultant is. But where am I starting these measurements from? And the answer to that is right where we started the whole problem, right at the location of the car, which is right in the middle. So it tells me from that location you want to go up 226.8. This is going to be kind of rough, but I'm just going to eyeball it. And I'm going to go over 95.3. So this is my 226.8 newtons. And this is my 95.3 newtons. And if I follow those directions that I just came up with, and I connect them tip to tail, then that will tell me, or give me, I don't like the way I do that, let me try again. That will give me my result. And does that resultant kind of match what we anticipated back at the beginning of the problem? Yeah, I guess so. It looks pretty close to where I was guessing the resultant would be. Well, we're doing great, but we're not done yet because we actually haven't found the resultant yet. Okay? So we know where it is and we know the components, but now this is a much easier problem because this is like back with our first scenario. We have two vectors that meet at 90 degrees. Can we find the resultant? Of course we can. We're experts at this. So how do we go about doing that? Well, if we're looking at that red resultant triangle, we're going to say, oh, a squared plus b squared equals c squared. Or in other words, 226.8 newtons squared plus 95.3 newtons squared is going to give us the resultant squared. When I solve for the resultant turns out to be 246 newtons in length. So I know this is actually 246 newtons of length. Well, all that's left to do is find the direction of this. So what I'm going to do is I'm going to find this angle right here. And using the similar process that we've learned a couple days ago, we'll say that the tangent of theta is the opposite over the adjacent side. opposite over adjacent. Opposite being 95.3 newtons, and the adjacent being 226.8 newtons. Through the magic of our calculator, the angle comes out to be about 23 degrees. But be careful. If this is right here, 23 degrees, is that the direction that the resultant is pointing? And a lot of the people in the class are saying, no, that's not really the direction the resultant is pointing. Remember, this line here, the 226.8, is straight up at, straight at 90. So if this is straight at 90, then from this line all the way over to the blue line, that's 90 degrees. So what way is the resultant really pointing? The resultant's really pointing 90 degrees minus 23 degrees, or in other words, it's pointing at about 67 degrees. So the angle from the blue to the resultant is 67. So the bottom line is, when you talk about this resultant, you're going to say that the resultant is 246 newtons at 67 degrees. And you've just gone through a pretty big problem with many steps, although each of the steps individually is something that you can probably handle. It's just a lot when you put it all together. So for today, physics.